MaskedMimic. It's tackling physics-based character control, a notoriously tricky area. The authors claim a unified model capable of handling diverse control modalities. What's the core innovation here, from your perspective?
The cleverness lies in framing the problem as motion painting. Instead of training separate controllers for walking, interacting with objects, responding to text commands, etc., they train a single model to fill in missing parts of a motion sequence. You give it partial information, a few keyframes, some text instructions, an object's location, and it generates a complete, physically plausible animation. So instead of meticulously crafting reward functions for each behavior, they're leveraging a more data-driven approach. How does the masking process work in training? What kind of data are we talking about?
The training data is a mix of motion capture data sets, a mask for diverse human movements, human ML3D for text-labeled motions, and SAM-MP for object interactions. They randomly mask parts of these motion sequences, sometimes entire joints, sometimes just keyframes, sometimes the text description. The model learns to reconstruct the full motion from these incomplete inputs. This random masking forces the model to learn robust representations and generalize better.
That's interesting. The paper mentions a two-stage process. Can you elaborate on that?
First, they train a fully constrained motion tracking controller using reinforcement learning. This controller is given the complete target motion and learns to reproduce it. Then, this fully constrained controller acts as a teacher for the second stage. The MaskedMimic model, the partially constrained controller, is trained via behavioral cloning, DDAGger, to mimic the teacher's actions, but only given the masked input.
So the first stage is essentially building a strong foundation, and the second stage is about generalization and flexibility. What architecture did they choose for MaskedMimic?
It's a conditional variational autoencoder, CVAE. The VAE aspect is crucial because it allows for multiple plausible solutions to a given set of partial constraints. The model doesn't just output one specific motion, it learns a distribution of possible motions, making the results more natural and varied. The prior in the VAE is a transformer network, allowing it to handle the multimodal inputs, keyframes, text, objects.
The paper highlights goal engineering as a key aspect of the user interface. What does that entail?
It's about specifying high-level goals instead of detailed trajectories. Instead of painstakingly keyframing every joint movement, you might just say, walk to that chair and sit down. The user provides partial constraints, and MaskedMimic figures out the physically realistic way to achieve those goals. They demonstrate this with tasks like path following, joystick steering, and object interaction.
The results seem impressive. What were some of the key performance metrics they used?
They evaluated success rates and error metrics, like MPJP, mean per joint position error, for various tasks, including full body tracking, VR tracking, using only head and hand data, and locomotion on irregular terrain. MaskedMimic consistently outperformed existing methods, especially in its ability to generalize to unseen motions and environments.
Did they address any limitations?
Yes, they acknowledge some jittering in the generated motions and difficulties with highly dynamic movements. They also point out that the goal engineering process, while more intuitive than traditional methods, could still be improved by automating it further.
How does this compare to other approaches that use latent spaces for motion control?
Many methods use latent spaces to represent different skills or behaviors. However, these latent spaces are often abstract and not easily controlled by a user. MaskedMimic's approach is more intuitive because the partial constraints are directly grounded in the data and easily understood by the user.
What about the text-to-motion aspect? How well did that work?
The text-to-motion capabilities showed promise for simpler actions, but struggled with more complex multi-step instructions. This suggests limitations in the model's ability to reason over longer time horizons.
So the temporal aspect is a potential area for future work.
Absolutely. Improving the temporal coherence of the generated motions, especially for complex tasks, is a key area for improvement. Also, automating the goal engineering process and extending the model to handle dynamic environments and multi-agent interactions are important next steps.
The paper mentions using a transformer architecture for the prior in the VAE. Why was that a good choice?
Transformers excel at handling sequential data and capturing long-range dependencies. In this case, the transformer allows the model to effectively integrate information from different modalities, keyframes, text, objects, and generate temporally coherent motions.
The use of D-Dagger for behavioral cloning seems standard, but what about the specific training techniques they employed to improve stability and performance?
They used several techniques: structured masking to maintain temporal coherence, Kyle scheduling to balance reconstruction and latent space regularization, episodic latent noise for smoother transitions, and incorporating observation history to improve long-term reasoning.
So overall, MaskedMimic presents a compelling approach to physics-based character control. It offers a more intuitive and flexible interface while achieving strong performance across a range of tasks. Thanks for breaking it down.